Have you ever wondered what would happen to the Earth if the sun suddenly became a black hole? Would we all just disappear? Would the Earth tumble and tumble nearer to the event horizon until we inevitably were crushed and spaghettified? Would aliens from another part of our universe travel through this passageway to our neck of the cosmos? What if I told you we would be just fine? But wait, how could a tiny speck of dust like our own planet survive against such a massive force of outer space? Welcome to the world of black holes. The answer lies in one single word: mass. The sun and the black hole are both made up of matter and therefore contain a mass. Now obviously the appearances of both these two objects is strikingly different. One is a common sight to see that provides solar energy to our planet and our biosphere, and the other right out of a sci-fi movie. But the important concept to grasp is that the universe will work the same way with either thing sitting at the center of our solar system. Plug the black hole's identical mass into Newton's law of gravitation, and you'll find that it exerts the same force on our tiny home planet as our sun. So what does separate our home planet, the Earth, or our sun, from this black hole? Take the Earth, for example. We can send out spacecraft and even humans out of our gravitational well and into orbit, and then land them without the Earth's gravitational pull crushing them. This is a rather impossible scenario for a black hole. At its core lies a point of amazing density called the singularity. This singularity bends the curvature of space-time so significantly that at some point, some distance away, not even light can escape. Hence the term black hole. Although what you find is that even though a black hole is a matter-crushing center surrounded by a dark envelope, it still has escape velocity. We can calculate our own escape velocity using our planet's mass and radius. After rearranging the variables a bit, you can find the radius of a black hole using just its mass and its escape velocity. The speed of light. So if nothing, not even light, can escape from a black hole, what happens to the matter that falls in? Well, as more matter falls into a black hole, its mass increases, so that quantitative aspect of the universe is conserved. But what happens to the information that falls into a black hole? The ones and zeros, as you can imagine them, the makeup of the very particles themselves. Do they just disappear? This was the hypothesis that most scientists had at first about black holes, yet it violated a fundamental law of the universe that states that information is conserved, much like energy. This created what became known as the information paradox, and this paradox fueled the fire to view the universe and black holes from a revolutionary perspective. If you look at my desk in my room, books, papers, and other items are randomly strewn across the wood surface. There exists a lot of hidden information on my desk, but nothing's been deleted. No information has just disappeared by being thrown around. The same was found to be true with black holes. The information wasn't simply deleted from the universe, it just became immensely harder to retrieve. Thus, entropy applied to black holes conserved the information in the universe. To demonstrate exactly how a black hole's entropy was related to its other properties, a situation was calculated in which bits of information or mathematically thrown into a black hole using the rearranged escape velocity equation? Perhaps the answer would seem obvious. Increase the stuff inside the volume of a black hole, and that volume will increase. Before accepting this as common knowledge, though, let's think back to my messy desk. If I described the 5 red pens that I kept in my pencil case with words accessible to the exterior, doubling that number to 10 would require twice the surface area and not twice the volume to write the extra words. And the same thing was found with black holes. If you increase the information that you threw into a black hole, the surface area would increase with it, not just the volume. And indeed, with the help of a little fancy mathematics, the result came. S, the entropy of a black hole, was proportional to A, its surface area. The fact that added information increased the surface area of a black hole in a linear relationship meant that somewhere, somehow, on the surface of a black hole, its threshold, its event horizon, tiny bits of information were stored in quantum cells. This was shocking, but the effects don't even stop there. Leonard Susskind, a physicist at Stanford University, took ideas from Gerard de Hooft on the implications of entropy area being related and string theory. What Gerard de Hooft had proposed referred to this idea of a 3-dimensional space being described at some 2-dimensional border. It was as if all the information you needed to describe the universe was located on some cosmological boundary. This model closely resembled the mechanism of a hologram, a 2-dimensional surface being blown up into a 3-dimensional object. And so it was named that, the holographic principle, and it provided one of the coolest ways to look at the universe in a new perspective. It is simply amazing that such an unintended result stemmed from curiosity and a different subject, and that this discovery was so unexpected. The holographic principle is one of the most interesting ways to view the universe, and mathematics continues to be the tool we use to probe the universe's inner mechanisms, and we are invariably rewarded with novel findings. Perhaps there are tweaks to be made with the holographic principle, and perhaps the principle becomes completely inconsistent with all known theories of science. But the main point is that we can only move forward in learning more and in letting our curiosity steer our journey deeper and even deeper into the beautiful complexity of our universe.